Okay, how's everybody doing? Professor Brian back with another installment of Workout Wednesday. Today, I wanted to focus on acid-base equilibrium, specifically looking at different ions on and their effect on the pH and being able to rank them, whether it be basicity or acidity. I think we need to be able to do all of that given a particular situation. So let's take a quick look. I have uploaded this as a worksheet. It is chapter 16. It's underneath chapter 16 handouts. And I would like to talk a little bit about these and what effect they would have. And then also talk a little bit about can we rank them if necessary. So we've been given 5 ions. We have been given nitrate. Again, nomenclature is always important. Carbonate. Potassium positive ion, iron 2 plus, and aluminum 3 plus. Okay, so when we talk about effect, the first thing that we need to be aware of, and I'm writing these down for us. Okay, so when we talk about the effect of each of these, the main thing that we need to be aware of is what is the conjugate, if there is a conjugate, acid or base, and how does the conjugate act? What kind of acid or base is the conjugate? So when we see NO3, the first thing that we should think about is we should be able to recognize immediately that NO3 is the conjugate base. So we can just put a CB above it. It's the conjugate base of a strong acid, and that strong acid is HNO3, nitric acid. So remember that the conjugate base of a strong acid has no effect on pH. It is neutral. Very important to be able to recognize that. And you can write that out as a statement. The conjugate base of a strong acid is neutral. Neutral, or you could say no effect on the pH. Okay, moving forward. Carbonate, so CO3 2 minus. If we think about this, this is the conjugate base of a weak acid, a weak polyprotic acid. So we have carbonic acid and bicarb, right, which is 2 acids, so 1 proton, and then you can lose the second one. Because this is the conjugate base of a weak acid, it does have an effect on pH because it is also considered a weak base. Therefore, it is basic, and the effect would be to increase pH, right? We'll have a small increase of pH if we looked up the Kb, which is based upon the Ka of these 2 acids. So it will be basic, and we should see an increase in pH. And we're going to talk a little bit in a second about the magnitude of that basicity, like where, like how can we rank the magnitude, okay? So let's take a look at potassium ion. So potassium ion is the conjugate acid, effectively. Well, not necessarily. I don't want to confuse you. So K is an ion that is associated with a strong base, KOH, right? So KOH is a strong base. The conjugate acid, when KOH is involved, is going to be the K. So you can kind of say that, but H2O is a better conjugate acid. So remember, when we write out hydroxide in solution, remember, we are writing out OH minus plus H2O, which creates OH minus and H2O. So don't get confused. The conjugate acid here is effectively water, not K plus. So K plus is not technically a conjugate acid, but it is the ion that is associated with a strong base. And since a strong base, by definition, dissociates completely, K plus should be neutral and therefore have no effect. So K plus, no effect, strong base. Okay, now let's take a look at your transition and post-transition metals. They give us iron 2 plus. So the iron 2 plus ion, remember, when we're dealing with transition metals that have multi-charged transition metals specifically, these are acidic, and therefore they decrease the pH. And remember, we talked about how that occurs, right? We talked about how that occurs. We talked about iron 2 plus having an interaction with the electron density of the water molecule, which is already polar, and we see that we end up with partial positive charges on the hydrogen already, and the iron is pulling that electron density towards itself and making this more acidic. So we're essentially making water more acidic than it normally would be, right? Remember the KW? We're making water more acidic by adding in the iron ions. And the same thing occurs with aluminum. We should see a decrease in pH because adding aluminum creates this same environment. The partially negatively charged oxygen is going to be interacting. Okay, so now if I ask you to rank them, and we can go from most basic to most acidic and vice versa, right? You should be able to do both of these. So the question doesn't ask that, but I'm asking you to be able to do both of these. The most basic in this particular case has to be the only one that is basic in solution. So that's pretty easy, right? CO3 2 minus is the most basic. Now, as it pertains to the neutral ones, both of these effectively the same, right? So it doesn't really matter the order on the neutral molecules. But now we end up with the part where we have to do some deduction and we have to do some reasoning, okay? Both of these ions are in fact acidic. Both of them decrease pH, but if we needed to rank them on which one is the most acidic is generally going to be the one with the higher charge, right? Higher charge. So most acidic when we're dealing with the transition, post-transition metals, transition metals and post-transition metals. Higher charge, more acidic. Therefore, iron 2 plus should be ranked, and then aluminum, because a stronger positive charge pulls in more electron density, pulls that electron density further towards itself, which makes the proton more acidic. So aluminum will be your most acidic. So this is a very good example of the type of problem from an understanding standpoint. Remember, this doesn't really involve any of the mathematics of the acid-base equilibrium. This really just involves the understanding of how each of these would occur. Another thing that you also have to be able to do is then from that be able to write again what these do. So for example, I want to just do two examples since there's only the one that's basic. Writing exactly what carbonate is going to do in a water solution. So remember, we have the formation of the conjugate acid, carbonate, bicarb, excuse me, and the creation of hydroxide ion, which is what makes it basic. So this is your breakdown. Remember, this is Ca, Cb, and this is your acid and base. Now, if we want to take a look at iron 2 plus with water, we are going to see it become acidic. And normally what you see here, and let me rewrite this for you. Normally what you see here is you see your metals involved in a complex, and that complex is octahedral plus water, which ends up making a 3O plus, which is the conjugate acid in this case, plus another complex, which is iron H2O, 5 of them with an OH, and we are dealing with a molecule that is +1. And again, the 2 plus can be written over here if you like. So here is an example of the iron dissociation, or the acid-base effect of the iron, creating H3O plus, which is the conjugate acid in this case. Here we have the conjugate base. Here we have the base, and here this is acting as an acid by making one or more of these protons associated with the complex acidic. Okay. All right. Any questions? Again, you know where to reach me. Feel free to reach out, comment on the video if necessary, and or send me an email.